This is Euclid Book 10, proposition number 28. And here is the illustration, right here. Okay, let's get into this, shall we? To find medial straight lines commensurable and square only, which contain a medial rectangle, let the rational straight lines A, B, and C, commensurable and square only, be set out. Okay. So all three of these lines are rational. Okay? They're all rational, and they're only commensurable in square. In other words, there is no number that will divide all three of these. But if you squared all three of these, there is an area that will divide all three of those areas. Okay. And I think we've pretty much established that over the last 20 or 30 videos from Euclid Book 10. Okay. Let D be taken a mean proportional between A and B. Okay. So D is a mean proportional between A and B, and this is by Euclid Book 6, proposition number 13. And let it be contrived that as B is to C, so as D is to E. As B is to C, so as D is to E. Okay. Since A and B are rational straight lines commensurable and square only, okay, so these two are rational lines, but they're only commensurable when they're squared. In other words, no number is going to divide A and B. That'd be like trying to divide 8 and 9. Not going to happen. Okay. Therefore, the rectangle A and B, that is the square on D, which is by Euclid Book 6, proposition number 17, is medial. So, in other words, you're going to have a rectangle. Two sides of that rectangle are going to be the length of A. Two sides of that rectangle are going to be the length of B. And the area inside of that is going to be exactly the same as another area. Now, what other areas are going to be the same as? Well, the area is D. We're going to make a square out of D. In other words, D is going to have four sides, and all four sides of D are going to be the same length as D. So in other words, you'll have a D, another D, another D, and another D. And the area inside of that will be the same area as the rectangle we just formed a few minutes ago. And if you want to draw that up and you want to put it on YouTube, you can go right ahead, and I'll leave a description of it right down here below just for you. Okay? Now, if the area in the rectangle of A and B is the same as the square on D, then it's medial because of Euclid Book 10, proposition number 21. That's important to know. Therefore, D is medial. And since B and C are commensurable and square only, and as B is to C, so as D is to E, okay. B and C here are commensurable and square only. In other words, you have to square both of these in order to get them to be commensurable. Okay? And as B is to C, so as D is to E. Okay? Therefore, alternately, as B is to D, so as C is to E. As B is to D, so as C is to E. Okay, that's alternately. But as B is to D, so as D is to A. Oh boy. So as B is to D, so as D is to A. Okay. Therefore, also as D is to A, so as C is to E. As D is to A, so as C is to E. D is to A as C is to E. Okay. Therefore, the rectangle AC, so in other words, now you're going to take the lengths of AC, you're going to make a rectangle out of them. So therefore, the rectangle will have two sides the length of A and two sides the length of C. And the area inside of that is going to be equal to the area of something else. Now, what is it equal to? Well, now you're going to take the sides of D and E. Okay, so now you're going to have a rectangle, two sides of which are going to be the length of D, two sides of which are going to be equal to the length of E. Okay, so two sides D, two sides E. The area inside that rectangle is going to be the same area as the rectangle we made a few minutes ago. And this is by Euclid Book 6, proposition number 16. But the rectangle AC is medial. Therefore, the rectangle DE is also medial. And that's by Euclid Book 10, proposition number 21. Therefore, medial straight lines commensurable in square only have been found which contain a medial rectangle. Wow. Okay. But here's the kick. Not only does this thing have a proof, but it has a couple of lemmas. Surprise, surprise. You ready for some lemmas? And no, I didn't say lemons, I said lemmas. Big difference. One's not as sour, although both of them are very tough. Lemma number 1. To find two square numbers such that their sum is also square. Here's the diagram for this one. Okay. Let two numbers A, B, B, C. Okay. So now we have AB, which is one number, and BC, which is the second one. Okay. Now they've been set out, and let them either be both even or both odd. Okay, so in other words, we could have, say, like the numbers 8 and 4, or we could have, say, like the numbers 5 and, well, how about 7 and 5? Either way. Okay. Then since whether an even number is subtracted from an even number or an odd number from an odd number, the remainder is always even. This is by Euclid Book 9, propositions number 24 and 26. Therefore, the remainder AC is even. AC is an even number. Okay. Let AC be bisected by D. Well, if AC here is bisected by D, then that means that AD is going to be the same length as DC. That's the first thing it's going to mean. Let AB, BC also be either similar plane numbers or square numbers, which are themselves also similar plane numbers. Now the product of AB and BC, so in other words, you're going to multiply the length of AB by the length of BC. That's what they call a product. Okay? Now the product of AB and BC together with the square on CD, so now you're going to have to take CD and you're going to have to make a physical square out of it. And so all four sides of that square are going to be the length of CD. Okay. So you've multiplied the length of AB times the length of BC, and now you're going to multiply that number times the area inside the square of CD. And when you do, what you're going to get is the amount of area you would find in the square on BD. Now, what does that mean? Okay, we're going to take BD and we're going to make a square out of that. And so what's going to happen is you're going to have four sides of a square. Each one of those four sides is going to measure the length of BD. That's what's going to happen. And this is by Euclid Book 2, proposition number 6. And the product of AB and BC is square, inasmuch as it was proved that if two similar plane numbers by multiplying one another make some number, the product is square. And this is by Euclid Book 9, proposition number 1. Therefore, two square numbers, the product of AB and BC, and the square on CD, have been found which, when added together, make the square on BD. Okay. So now we're saying the two square numbers AB and BC. Okay, we've got two square numbers AB and BC. We're going to multiply them together. Okay? And when we do, and then we add it to the square on CD. Okay, so first we multiply these two numbers together, and then we add that value. Once we multiply, we add that value to the square area contained by the line CD. If you add all that together, then it forms the square on BD. Okay? And it is manifest that two square numbers, the square on BD and the square on CD, have again been found such that their difference, the product of AB and BC, is a square whenever AB and BC are similar plane numbers. But when they are not similar plane numbers, the two square numbers, the square on BD and the square on DC, have been found such that their difference, the product of AB and BC, is not square. Wow, that's lemma number 1. Let's go on to lemma number 2. Now this one gets more interesting. As if we didn't have enough. Dang it. As if we didn't have an already whacked out diagram, there's another one. Okay, so lemma number 2 decides to find two square numbers such that their sum is not square. For let the product AB and BC, as we said, be square. Okay, so you take AB, you multiply it by BC, and its product will end up being a square. And let CA be even. Okay, so now we're going to say that the length of CA is even. Okay. And let CA be bisected by D. Okay, so we have the length of CA, it's bisected by D, and according to this, that the length of AD is going to be the exact same length as the length of DC. I know that's not what it looks like here, but if you were to draw this out for real, that's what it would look like. Okay. It is then manifest that the square product of AB and BC together with the square on CD is equal to the square on BD. And that is by lemma number 1, which we just did 5 seconds ago. Let the unit DE be subtracted. Okay. So we already know that Euclid called the number 1 a unit, so we're going to subtract 1. Okay. Therefore, the product of AB and BC together with the square on CE is less than the square on BD. Okay. So what is the square on CE? Well, that's when you take CE here, you take that length and you make a square out of it. And all four sides of that square are going to have the same length, CE. That's what that means. Okay? And so therefore, now, what is the square on BD? Well, we have the length of BD here, okay? And what's going to happen is you're going to make a square out of it. And all four sides of that square are going to be the length of BD. That's what that means. Okay. A little less confusion for you. I say then that the square product of ABBC together with the square on CE will not be square. So you take AB and BC, you multiply them together, and whatever product they have, which ends up being square, if you add it with the square on CE, then the total of that will not be square. For if it is square, it is either equal to the square on BE or less than the square on BE. So, it has to either be equal to the square on BE or less than the square on BE. Okay. But cannot any more be greater lest the unit be divided. So if that whatever product is greater than BE, the square on BE, okay, if that original product is greater than the square on BE, then you're going to divide 1. You can't divide 1. Okay. First, if possible, let the product of AB and BC together with the square on CE be equal to the square on BE. And let GA be double of DE. Okay, so now we're going to say that GA is double of DE. So, if DE is 1, then we can say that GA is 2. Okay, we're going to say hypothetically GA is 2 and DE is 1. Let's see what the problem is. Since then the whole AC is double the whole CD, so now we're going to say that AC is double the length of CD. Okay, now we're going to say that AC is double the length of CD. And in them, AG is double of DE. Therefore, the remainder GC is double the remainder of EC. Okay, so GC is double EC. So now we're going to say that GC is double the length of EC. Now this is going to lead to a problem here in just a second. Therefore, GC is bisected by E. Now we're going to say that E bisects GC. And now we're going to be able to say that GE is the same length as EC. There's going to be a problem in a second. I can tell you that right now. Therefore, the product of GBBC together with the square on CE is equal to the square on BE. And this is by Euclid Book 2, proposition number 6. Okay, so GBBC. So now we're going to multiply GB and BC. We're going to multiply both of those. And once we get that total, we're going to set it off to the side. Then we're going to figure out what the square on CE is. So what are we going to do? We're going to take the length of CE. We're going to make a square out of it. And all four sides of that square are going to be equal to the length of CE. That's what we're going to say. So now we take that product, we set off to the side, we're going to add it to that square area of CE, and what are we going to get? According to this, we're going to get the square on BE. So now, we have to take the line length of BE, and we have to make a square out of it. And all four sides of that square are going to be the length of BE. So, we had two lines, we multiplied their lengths together, then we added them to a square, and that total is supposed to be equal to the square we just formed from BE. Okay. Therefore, the product of GBBC together with a square on CE is equal to the product of AB and BC together with a square on CE. Okay, so now we're saying that we're going to take the line lengths AB and BC. We're going to take these two line lengths here, we're going to multiply them together, and then we're going to add them to the square area of CE, which is this right here, and then we can say that the product of GBBC together with the square on CE is equal to the product of ABBC together with a square on CE. And if the common square on CE is be subtracted, it follows that AB is equal to GB. So now, we're going to say that the length of AB is equal to the length of GB, which is impossible. Therefore, the product of ABBC together with a square on CE is not equal to the square on BE. And you can draw all this out, you can see it for yourself. I say next that neither is it less than the square on BE. For if possible, let it be equal to the square on BF. So now we're going to take B, and I don't see an F. Oh, that's not a P, that's an F. Okay, so I got the diagram a little wrong. So, if the product of AB and BC together with the square on CE is less than BE, then that whole amount I just said will be equal to the square on BF. So now we're going to have to take BF here, and then we're going to have to make a square out of it, and all four sides of that square are going to be the length of BF. Okay. And let HA be double of DF. So now we're going to say that AH is twice the size of DF. Okay. Now we'll again follow that HC is double CF. So now we're going to have to say that HC is double the length of CF. So this length here is going to be double the size of this length right here. Okay? So that CH has also been bisected by F. Okay? So now we're going to say that the line CH was bisected by F. This is going to start leading into problems real quick. And for this reason, the product of HBBC together with the square on FC is equal to the square on BF. Well, what you do is you take the line lengths of HB and BC, you multiply them together, and then you find the square on CF. In other words, you take the length of CF, you make it into a square, and all four sides of that square are going to be the length of CF. So that whole total is going to equal BF. Okay? Well, that not BF, but the square on BF. Okay? So in other words, you're going to take BF, You're going to make it into a square. All four sides of that square are going to be BF. This is by Euclid Book 2, proposition number 6. But by hypothesis, the product of AB, BC together with the square on CE is also equal to the square on BF. Thus, the product of HB, BC together with the square on CF will also equal the product of AB, BC together with the square on CE. And apparently that's absurd. You could draw all this out for yourself, and if you decide to do so, you can go ahead and leave it down here in the comments below, and I'll post a link. Therefore, the product of AB, BC together with the square on CE is not less than the square on BE, and it was proved that neither is it equal to the square on BE. Therefore, the product of AB, BC together with the square on CE is not square. And that ends the two lemmas. Alright, I will tell you more in a future video. Stay tuned.